Welcome back to our podcast, Ancient Earth Documentary. 4.5 billion years ago, lightning didn't just flash across the sky occasionally. It exploded through Earth's atmosphere in numbers that would make today's worst thunderstorms look like camera flickers. We're talking about somewhere between 1 billion and 5 billion lightning strikes every single year, with up to 1 billion of those slamming directly into the ground. For context, modern Earth sees around 560 million strikes annually. Ancient Earth experienced nearly 10 times that amount, and the difference wasn't just scale, it was violence. The sky back then wasn't the blue canvas we know. It was a chemical experiment gone mad, thick with carbon dioxide, choked with volcanic ash, and superheated to temperatures that would make Death Valley feel like a freezer. Every element of that primordial atmosphere conspired to create the perfect conditions for electrical chaos. But here's what most people miss when they picture ancient Earth. The lightning wasn't random. It was systematic, driven by forces we can measure, track, and understand through the fingerprints left behind in ancient rocks. Those fingerprints tell a story that rewrites what we thought we knew about our planet's electrical history. The connection between lightning and atmosphere might seem obvious now, but the mechanics reveal something profound. When that Mars-sized object crashed into early Earth and tore away the chunk that became our moon, it didn't just create a satellite. It ripped open the planet's interior and released a torrent of gases that had been locked beneath the crust. Carbon dioxide flooded the atmosphere in concentrations we can barely comprehend today, somewhere around 1,500 parts per million in the early Carboniferous, compared to roughly 420 parts per million now. That CO2 didn't just sit there. It trapped heat like a blanket made of greenhouse gas, pushing global temperatures to levels where thunderstorms weren't occasional weather events. They were the default state. Scientists discovered they could actually use ancient CO2 levels as a proxy for lightning frequency, because the relationship is that direct. More carbon dioxide equals higher temperatures, which equals more evaporation, which equals more unstable air masses colliding and generating the static charge that becomes lightning. The math is almost elegant in its brutality, but temperature alone doesn't explain the full picture. You need to understand what else was happening in that ancient sky, and this is where volcanic activity enters the story with the subtlety of a sledgehammer. Ancient Earth wasn't just volcanically active. It was a planet-wide forge, with magma chambers rupturing through a crust that hadn't fully solidified. When volcanoes erupt today, they occasionally produce what scientists call volcanic lightning or dirty thunderstorms. When volcanoes erupted on ancient Earth, they created electrical displays that modern instruments can barely comprehend. The 2022 eruption of Hunga volcano in Tonga gave us a glimpse. That single eruption produced nearly 200,000 lightning flashes, peaking at more than 2,600 strikes per minute. The volcano was ejecting 11 billion pounds of material every second into a plume that rose 58 kilometers high. Lightning was detected 20 to 30 kilometers above sea level, far higher than typical storm lightning. Now imagine that happening not once as a spectacular exception, but continuously across dozens or hundreds of active volcanic systems. That was Tuesday on ancient Earth. Volcanic lightning operates differently than storm lightning, though both rely on the same fundamental physics. When ash particles collide and fragment within a volcanic plume, they generate static electricity through friction. The faster and more violently the eruption, the more intense the electrical charge becomes. Ancient volcanoes erupted with explosive force that modern volcanoes rarely match because the Earth's interior was significantly hotter. The mantle churned more vigorously, driving more frequent and more powerful eruptions. Research on hydrogen cyanide concentrations shows that volcanic lightning produced concentrations an order of magnitude larger than general atmospheric lightning. This matters because those nitrogen compounds, created when lightning rips apart N2 molecules, played a crucial role in the chemical reactions that eventually led to life. But we're getting ahead of ourselves. First, you need to understand just how different the air itself was. The atmosphere of ancient Earth underwent transformations so dramatic that calling them changes feels inadequate. They were revolutions, complete restructurings of the chemical composition that determined everything from the color of the sky to whether organic molecules could form. During Earth's first billion years, the atmosphere was a toxic soup dominated by hydrogen and helium compounds. These lighter elements eventually escaped into space because Earth's gravity couldn't hold them against the solar wind, leaving behind an atmosphere of methane, nitrogen, ammonia, and trace amounts of oxygen. But that trace oxygen is where the story gets interesting. Before photosynthesis evolved, oxygen existed in Earth's atmosphere only through photolysis, the process where ultraviolet radiation, and possibly lightning itself, split water molecules and carbon dioxide into their constituent parts. This process was spectacularly inefficient, producing maybe 1% of the oxygen we have today. Yet it was enough to begin a slow chemical transformation that would eventually enable the oxygen-rich atmosphere we depend on. Around 2.45 billion years ago, something shifted. The Great Oxygenation Event wasn't a single moment, but a drawn-out catastrophe or miracle, depending on your perspective, that saw atmospheric oxygen levels spike from nearly nothing to roughly 10% of current levels. Cyanobacteria had evolved photosynthesis and began pumping oxygen into an atmosphere that had no idea what to do with it. The oxygen immediately reacted with methane, with hydrogen sulfide, with dissolved iron in the oceans, creating the banded iron formations we still mine today. For nearly 2 billion years after that, oxygen levels stayed relatively stable and low. Then, around 540 million years ago, they began climbing again. This is when our story really accelerates, because this is when the atmospheric conditions align to create lightning on a scale that makes modern thunderstorms look polite. The Carboniferous period, stretching from about 359 to 299 million years ago, represents the peak of Earth's oxygen experiment. At the start of the period, oxygen made up roughly 20% of the atmosphere, similar to today. But over the next 50 million years, it climbed to 25%, then 30%, and by some estimates hit 35% during the late Carboniferous. To put that in perspective, modern firefighters know that fires become extremely difficult to control once oxygen concentrations exceed 23%. At 25%, even wet organic matter will burn freely. At 35%, the world was a tinderbox. This oxygen surge wasn't random. It was driven by the evolution of lignin, a complex organic compound that plants use to build their structural tissues. Lignin made trees possible, allowing plants to grow tall and rigid instead of flopping over like wet noodles. But here's the catch. When those lignin-rich plants died, the bacteria of the time couldn't break them down efficiently. The carbon-rich plant material just sat there in massive swamps, sequestering carbon instead of releasing it back into the atmosphere through decay. But because bacteria use oxygen when they break down organic material, and because they couldn't efficiently decompose lignin, that oxygen stayed in the atmosphere instead of being consumed. The result was a positive feedback loop. More plants produced more oxygen, which allowed more plants to grow, which produced more oxygen. The atmosphere became supercharged with O2, and with it came consequences that rippled through every ecosystem on the planet. Lightning frequency exploded during this period, though we need to be careful about how we understand that explosion. The correlation between oxygen levels and lightning isn't as straightforward as more oxygen equals more lightning. Instead, elevated oxygen levels changed how fires behaved, and fires leave evidence we can still examine today. Charcoal deposits in Carboniferous sediments are abundant, far more common than in earlier periods. These charcoal records, called fusane in coal deposits, represent the remains of wildfires that swept through the ancient forests with devastating regularity. Most of those fires were started by lightning strikes. When atmospheric oxygen sits at 16%, fires won't propagate at all. At 21%, our current level, fires ignite and spread readily under the right conditions. At 23% and above, fires become more frequent, more widespread, and exponentially more destructive. Anything that creates a spark can ignite even damp fuel. At the oxygen levels present during the late Carboniferous, lightning strikes didn't just start fires. They started infernos that could burn for months, consuming forests and creating charcoal deposits so thick we mine them as coal today. The presence of extensive charcoal deposits tells us two things simultaneously. First, that oxygen levels were elevated enough to support aggressive fire spread. Second, that lightning was frequent enough to provide the ignition sources for those fires. You can't have one without the other. The charcoal is fossil evidence of ancient lightning, preserved in rock layers that span millions of years, but oxygen levels tell only part of the story. Temperature played an equally critical role, and this is where the carbon dioxide connection comes full circle. The early Carboniferous was hot, with average global temperatures around 20 degrees Celsius or 68 degrees Fahrenheit. That's substantially warmer than today's average of roughly 14 degrees Celsius. Higher temperatures meant more evaporation from the massive swamps and shallow seas that covered much of the planet. More evaporation meant more water vapor in the atmosphere, and water vapor is the fuel that powers thunderstorms. The mechanism is straightforward once you see it. Warm, moist air rises rapidly, creating unstable atmospheric conditions. As that air rises and cools, the water vapor condenses into droplets. The process of condensation releases latent heat, which causes the air to rise even faster, creating powerful updrafts. Within these churning columns of air, ice crystals and water droplets collide, generating static electricity through friction. When enough charge builds up, it discharges as lightning. The warmer the planet, the more frequent and intense these thunderstorms become. During the Middle Carboniferous, something shifted. Temperatures cooled to about 12 degrees Celsius, comparable to modern averages. Carbon dioxide levels dropped from around 1,500 parts per million to roughly 350 parts per million. This wasn't gradual climate change. This was a crash, driven by the same lignin-rich plants that had supercharged atmospheric oxygen. As those plants died and formed coal deposits, they pulled carbon out of the atmosphere and buried it underground. The greenhouse effect weakened, temperatures fell, and climate models suggest Earth came dangerously close to complete glaciation around 300 million years ago. Lightning frequency would have declined during this cooling period, but it didn't disappear. The elevated oxygen levels ensured that thunderstorms, even if less frequent, remained powerful, and volcanic activity continued to add its own contribution to the electrical chaos overhead. The planet was cooling, but it was still far more electrically active than anything we experience today. Then came the evidence that really seals the case. Fulgurites. These are the physical scars lightning leaves behind when it strikes sandy soil. The discharge, carrying upwards of 100 million volts, propagates into the ground and instantly vaporizes and melts silica-rich sand. The result is a hollow, branching tube of glass that forms in about 1 second. Gases like CO2 get trapped in tiny bubbles within the glass, preserved for millions of years. By analyzing those trapped gases, scientists can determine soil characteristics during formation, which provides clues about ancient climate conditions. Fulgurites serve as lightning's permanent signature, scattered through geological layers like electrical fossils. The oldest confirmed fulgurite dates to the Permian period, around 250 million years ago, though older examples likely exist undiscovered. The presence and distribution of fulgurites in an area allows scientists to estimate lightning frequency over geological timescales. Find more fulgurites in a particular layer, and you know lightning was more active during that period. The Carboniferous and Permian periods are rich with fulgurite deposits, far more than later periods. This isn't sampling bias. It's evidence of an atmosphere that generated lightning with frightening regularity. Each fulgurite represents a single strike powerful enough to melt sand into glass, and there are thousands of them scattered through rock formations worldwide. Multiply those preserved strikes by the countless others that hit rock, water, or organic material that left no permanent trace, and you begin to grasp the scale. But perhaps the most compelling evidence comes from what that ancient lightning created. The amino acids, the organic compounds, the chemical building blocks that eventually became life. In 1952, Stanley Miller and Harold Urey conducted an experiment that became legendary in origin of life research. They filled glass tubes with water, methane, ammonia, and hydrogen, mimicking the composition of Earth's early atmosphere. Then, they blasted the mixture with electrical discharges to simulate lightning. At the end of the experiment, 15% of the carbon had formed organic compounds. 2% had become amino acids, the fundamental components of proteins. Lightning wasn't just illuminating ancient Earth, it was cooking up the chemistry of life itself, one strike at a time. That chemistry experiment didn't just prove a concept, it fundamentally changed how scientists understand the origin of life. Because if lightning could create amino acids in a laboratory, what was it creating across billions of years of electrical storms on ancient Earth? Phosphorus offers part of the answer. Every cell in your body needs phosphorus to function. It's in your DNA, your cell membranes, the molecules that store energy. Without phosphorus, life as we know it doesn't exist. But phosphorus is typically locked away in rocks, bound up in minerals that don't dissolve easily. Early life faced a serious problem: how to access this essential element when it was trapped in stone. Lightning solved that problem. When a bolt strikes ground and creates a fulgurite, it doesn't just melt sand into glass. It breaks down phosphorus-bearing minerals through extreme heat and chemical reactions. The glassy tubes weather over time, releasing bioavailable phosphorus into soil and water. Scientists estimate that early Earth's elevated lightning activity could have liberated massive quantities of phosphorus, possibly providing most of what primitive organisms needed to develop. The math is striking, with up to 5 billion lightning strikes per year, and a significant portion hitting phosphorus-rich ground. Ancient Earth was essentially running a planetary-scale chemical factory. Each strike contributed a small amount of accessible phosphorus, but multiply that by millions of years, and you get an accumulation that could have jump-started biological chemistry. This wasn't the only way lightning contributed to life's emergence. Nitrogen fixation represents another critical pathway. Modern life requires nitrogen for proteins, DNA, and countless other molecules. But atmospheric nitrogen is notoriously unreactive. It exists as tightly bonded N2 molecules that most organisms can't break apart. Lightning changes that equation. When a lightning channel rips through air at temperatures 5 times hotter than the sun's surface, it tears nitrogen molecules apart and combines them with oxygen, creating nitrogen oxides. These compounds dissolve in rain and fall to Earth as nitrates, which plants and microorganisms can actually use. Today, lightning produces an estimated 1 to 20 teragrams of nitrogen per year through this process. Some researchers argue it contributes more to the global nitrogen budget than fossil fuel combustion. Ancient Earth, with its dramatically higher lightning frequency, would have been fixing nitrogen at rates that dwarf modern levels. Early ecosystems may have depended almost entirely on lightning-generated nitrates before biological nitrogen fixation evolved. You're probably wondering how researchers actually measure something that happened hundreds of millions of years ago. The answer involves multiple lines of evidence that converge toward the same conclusion. Start with atmospheric modeling. Scientists can estimate ancient CO2 levels from geological proxies like paleosols, ancient soils preserved in rock. Those CO2 estimates feed into climate models that calculate global temperatures. Temperature directly controls convective activity, which generates thunderstorms. More heat means more convection, which means more storms, which means more lightning. The relationship isn't perfectly linear, but it's strong enough to provide reliable estimates. When researchers ran these models for the Carboniferous period, they found conditions that would have generated thunderstorms far more frequently than today. But models only tell part of the story. Charcoal deposits provide physical evidence that confirms what the models predict. Charcoal is fossilized evidence of fire, and fires need three things: fuel, oxygen, and ignition. Ancient Earth had extraordinary amounts of the first two. The vast forests of the Carboniferous provided endless fuel. Oxygen levels up to 35% meant even wet organic matter could burn. That leaves ignition, and lightning is overwhelmingly the most common natural ignition source. Volcanic activity can start fires, but volcanoes are geographically limited. Lightning strikes everywhere. The widespread distribution of Carboniferous charcoal, found in tropical wetland peats and nearshore sediments across multiple continents, points to a single culprit: constant lightning strikes igniting vegetation in an oxygen-supercharged atmosphere. The charcoal record reveals something else. Fire frequency tracks oxygen levels with remarkable precision. During periods when oxygen climbed above 23%, charcoal becomes abundant in the fossil record. When oxygen dropped below 19%, charcoal nearly disappears. This isn't coincidence. At 16% oxygen, fires won't propagate at all. At 21%, our current level, fires ignite and spread readily. At 23% and above, fire behavior changes dramatically. Everything becomes fuel. Even damp wood burns freely. A single spark can trigger conflagrations that consume entire ecosystems. Ancient Earth spent millions of years in this fire-prone state, and lightning provided the sparks. Consider what this means for the organisms living through these periods. Dragonflies with 2-foot wingspans, millipedes the size of cars, amphibians that could swallow a human whole. These creatures existed in an environment where lightning-triggered wildfires were constant background noise. Forest fires weren't rare catastrophes, but regular events that shaped evolutionary pressures. Species had to adapt to periodic burns, developing fire-resistant life stages or behaviors that allowed them to survive and recolonize burned areas. Some plants evolved thick bark. Others developed seeds that only germinated after fire. The ecological impact of frequent lightning and the fires it caused rippled through every aspect of ancient ecosystems. Then there's the atmospheric electricity itself, independent of fire. High oxygen concentrations change how electricity behaves in air. Oxygen affects electrical conductivity, breakdown voltage, and charge distribution in clouds. An atmosphere with 35% oxygen doesn't just produce more lightning. It produces different lightning. The bolts would have been more intense, carried more energy, and potentially behaved in ways that have no modern analogue. We can barely imagine what that looked like because we've never witnessed it. The closest comparison might be volcanic lightning, which creates electrical conditions outside the range of normal meteorological storms. Speaking of volcanic lightning, ancient Earth's heightened volcanic activity adds another dimension to the story. Volcanoes don't just erupt lava, they blast enormous quantities of ash, water vapor, and gas into the atmosphere. When volcanic plumes rise rapidly, friction between ash particles generates static electricity. The plume essentially becomes a giant thundercloud, except it's composed of rock fragments instead of water droplets. Discharge follows rapidly, creating what scientists call a dirty thunderstorm. These volcanic lightning storms can produce hundreds of thousands of strikes in a matter of hours. The January 2022 eruption of Hunga volcano in Tonga generated nearly 200,000 lightning flashes, peaking at 2,600 strikes per minute. That's faster than a machine gun fires bullets. At one point, the volcano was ejecting 11 billion pounds of material per second into a column that reached 58 kilometers high. The umbrella cloud that formed produced lightning 20 to 30 kilometers above sea level, far higher than typical thunderstorms. This represents the most intense lightning ever recorded by modern instruments. Now imagine that ancient Earth experienced volcanic activity orders of magnitude greater than today. Not just one Hunga eruption, but dozens occurring simultaneously across the planet. The Carboniferous and Permian periods saw extensive volcanic provinces that make modern volcanic zones look modest by comparison. Each major eruption would have triggered its own lightning storm, adding to the background meteorological lightning generated by normal weather patterns. The combined effect would have been a planet where electrical discharge was nearly constant. Stand anywhere on ancient Earth, and you'd probably see lightning flickering somewhere on the horizon at any given moment. The night sky wouldn't have been dark. It would have been strobing. This constant electrical activity had chemical consequences beyond what we've already discussed. Lightning produces more than just nitrogen oxides and phosphorus. Each discharge creates a complex cocktail of compounds through high-energy chemistry. Hydrogen cyanide forms when lightning passes through nitrogen and carbon-containing atmospheres. That might sound toxic, and it is, but hydrogen cyanide also serves as a precursor for amino acids and nucleotides. Research shows that volcanic lightning produces hydrogen cyanide concentrations an order of magnitude larger than regular lightning because volcanic plumes contain additional reducing gases. These compounds occurred fairly close to ground level, where they could interact with surface chemistry and potentially contribute to prebiotic synthesis. The picture that emerges is of a planet where lightning wasn't just common, it was transformative. It shaped atmospheric chemistry, drove nitrogen and phosphorus cycles, triggered ecosystem-altering fires, and potentially catalyzed the chemical reactions that led to life. Ancient Earth was essentially a giant electrochemical reactor, powered by atmospheric instability and cranked up to settings we can barely comprehend. Every thunderstorm was an experiment in organic chemistry. Every lightning strike was a potential factory for biological molecules. Over hundreds of millions of years, those experiments and factories produced results. The question isn't whether lightning contributed to life's emergence. The question is whether life could have emerged without it. The geology holds the receipts. When lightning strikes sand, it creates fulgurites. These are glassy tubes formed when electrical discharge melts silica-rich material in less than a second. Think frozen lightning, crystallized pathways where 100 million volts ripped through the ground. The tubes branch like inverted trees, hollow structures that preserve the exact moment of impact. Some fulgurites are found individually. Others occur in fields, suggesting repeated strikes in the same area over time. Dating fulgurites isn't straightforward. They don't contain the radioactive isotopes that make other rocks easy to timestamp. But researchers have developed clever workarounds. Gases, trapped in tiny bubbles within the glassy matrix, can reveal soil characteristics at the moment of formation. Carbon dioxide concentrations, for instance, hint at paleoclimate conditions. The surrounding rock layers provide context. Fossiliferous Carboniferous rocks overlying certain fulgurite deposits suggest formation during the Permian period, making them over 250 million years old. What makes fulgurites particularly valuable is their distribution. High concentrations in specific geological formations indicate periods of intense lightning activity. It's like finding shell casings on a battlefield. The density tells you how heavy the fighting was. Carboniferous and Permian rock layers contain fulgurite deposits that dwarf anything from more recent periods. The implication is clear. Lightning struck these ancient landscapes far more frequently than it strikes modern terrain. But fulgurites represent only ground strikes. Most lightning never touches the surface. Cloud-to-cloud discharges vastly outnumber cloud-to-ground strikes in modern storms. The ratio probably held true in ancient times as well. For every fulgurite preserved in the geological record, thousands of aerial discharges left no trace. The visible evidence represents a tiny fraction of total electrical activity. Charcoal deposits tell a complementary story. Fusaine, the geological term for fossilized charcoal, occurs widely in Carboniferous coal seams and sediments. Not until the early Carboniferous do we see extensive charcoal deposits in near-shore clastic sediments. By the late Carboniferous, charcoal was common or abundant across diverse environments, including tropical wetland peats. This represents the first geological period to experience extensive wildfire. Lightning ignites the majority of natural fires. Volcanic activity, meteorite impacts, and spontaneous combustion provide alternative ignition sources, but none match lightning's frequency or reach. The charcoal record essentially maps ancient lightning strike patterns. More charcoal means more fires mean more lightning. The Carboniferous charcoal deposits are staggering in scale, indicating wildfire occurrence far beyond anything documented in recent history. Here's where oxygen enters the equation again. Fire requires three elements: fuel, heat, and oxygen. Ancient Earth had abundant fuel in the form of vast forests. Lightning provided unlimited heat, but oxygen concentration determines whether ignition translates into sustained burning. Below 16% oxygen, fires won't propagate regardless of fuel or ignition source. At modern oxygen levels around 21%, fires ignite and spread readily. Above 23%, fire behavior changes dramatically. Anything capable of creating a spark becomes dangerous at elevated oxygen levels. Even wet organic matter burns freely above 25% oxygen. The practical upper limit sits around 30%, beyond which atmospheric chemistry becomes genuinely unstable. Carboniferous oxygen peak between 25 and 35%, depending on the specific time frame and location. That's an atmosphere primed for combustion. Picture a lightning strike hitting a Carboniferous forest during the oxygen peak. The bolt ignites dry vegetation instantly. Under modern oxygen levels, the fire might spread slowly, giving animals time to flee and potentially burning out at natural fire breaks. Under 30% oxygen, the same strike triggers an inferno. Flames race through the canopy. Green wood catches fire. Even damp undergrowth combusts. The fire doesn't creep. It explodes. These weren't small brush fires. They were landscape-altering conflagrations that could consume thousands of square kilometers before rainfall or geographical barriers stopped their advance. The charcoal record preserves the aftermath. Layers of fusaine represent catastrophic fire events, periodic resets that shaped ecosystem evolution throughout the Carboniferous and Permian periods. Lightning-caused fires created a feedback loop with the oxygen cycle. When forests burned, carbon stored in plant material oxidized back into carbon dioxide. This temporarily reduced atmospheric oxygen while increasing CO2. But the Carboniferous forests were so productive that photosynthesis quickly replenished oxygen, setting the stage for the next fire cycle. The planet oscillated between oxygen production and oxygen consumption, with lightning-triggered fires serving as the primary mechanism for the latter. The evolutionary implications were profound. Organisms had to adapt to a world where massive fires were routine rather than exceptional events. Some plants developed fire-resistant characteristics: thick bark, deep root systems, rapid regrowth after burning. Others evolved to depend on fire for reproduction, using heat to trigger seed release or eliminate competing vegetation. Fire became a selective pressure, as significant as predation or climate. Animals faced their own challenges. Mobility became essential. Species that could detect smoke and flee survived. Those that couldn't, didn't. The fossil record shows distinct changes in fauna composition across fire-heavy periods. Flight evolved multiple times during the Carboniferous, not coincidentally. Insects, pterosaurs, and eventually birds all developed the ability to escape ground-level threats by taking to the air. Lightning-caused fires may have accelerated the evolution of flight itself. The giant arthropods that characterized the Carboniferous period thrived partly because high oxygen levels enabled their inefficient respiratory systems. But when oxygen dropped during the Permian, many couldn't adapt. The same atmospheric shift that reduced lightning frequency also eliminated the creatures that had evolved in the lightning-scarred, oxygen-rich world. How do we know atmospheric oxygen actually reached these extreme levels? Multiple lines of evidence converge. Charcoal abundance indicates oxygen above the modern fire threshold. The size of fossil insects suggests oxygen concentrations that could support their oversized bodies. Geochemical models analyzing carbon burial rates and volcanic outgassing point toward oxygen peaks during specific periods. The chemistry of ancient soils preserved in rock formations reveals oxidation states consistent with elevated oxygen. Paleosol analysis provides particularly compelling evidence. When iron-rich soils are exposed to oxygen, iron oxidizes into distinctive minerals. The degree and depth of oxidation in ancient soils indicates atmospheric oxygen concentration at the time of formation. Carboniferous paleosols show oxidation patterns that can't be explained by modern oxygen levels. The chemistry demands higher concentrations. Plant evolution drove this oxygen revolution. During the Carboniferous, plants developed lignin, the complex organic polymer that gives wood its structure and strength. Lignin allowed plants to grow tall, competing for sunlight and creating the first true forests. But early bacteria couldn't decompose lignin efficiently. When trees died, their trunks fell into swamps where low oxygen conditions prevented decay. The carbon in those trees should have oxidized back into CO2. Instead, it stayed locked in plant tissue. Over millions of years, layer upon layer of undecomposed vegetation accumulated in swamps, eventually compressing into coal. This carbon sequestration removed CO2 from the atmosphere while allowing oxygen from photosynthesis to accumulate. The result was an oxygen spike unprecedented in Earth's history. Eventually, bacteria evolved lignin-degrading enzymes. Once decomposition caught up with plant death, carbon burial slowed. Oxygen production no longer outpaced oxygen consumption. Atmospheric oxygen declined from its Carboniferous peak. The Permian period saw oxygen drop from 30% to around 15%, lower than modern levels. This decline coincided with the worst mass extinction in Earth's history. Temperature fluctuations played their role throughout. Early Carboniferous temperatures averaged around 20 degrees Celsius. By the Middle Carboniferous, global temperatures had dropped to 12 degrees Celsius, comparable to today. Carbon dioxide declined from 1,500 parts per million to approximately 350 parts per million. The cooling resulted from carbon burial during coal formation. As plants pulled CO2 from the atmosphere and stored it underground, the greenhouse effect weakened. This cooling brought Earth dangerously close to global glaciation around 300 million years ago. Ice sheets advanced from the poles. Sea levels dropped. Climate became more variable with pronounced seasons. These temperature swings affected lightning frequency through their impact on convection and storm intensity. Warmer periods generated more violent thunderstorms. Cooler periods saw reduced convective activity. The interplay between CO2, temperature, oxygen, and lightning created a complex feedback system. High CO2 meant high temperatures. High temperatures meant more thunderstorms and lightning. Lightning produced nitrogen oxides that fertilized plant growth. More plants meant more oxygen production and carbon burial. Carbon burial reduced CO2, cooling the planet and eventually reducing lightning frequency. Then volcanic activity or reduced plant burial would increase CO2 again, restarting the cycle. This wasn't a smooth, gradual process. Climate and atmospheric chemistry lurched between extremes over millions of years. Lightning frequency rose and fell accordingly. The Carboniferous represented one extreme, an oxygen-rich hothouse with near-constant electrical activity. The Permian represented another, a drying, cooling world where oxygen crashed and many lightning-dependent chemical cycles faltered. The transition between these states wasn't gentle. Geochemical evidence suggests rapid changes in atmospheric composition over relatively short geological timescales. Thousands of years might separate radically different atmospheric conditions. Organisms adapted to one regime faced extinction when conditions shifted. The Permian Triassic extinction event eliminated over 90% of marine species and 70% of terrestrial vertebrate species. Multiple factors contributed to this catastrophe. Volcanic activity released massive amounts of CO2. Ocean chemistry changed dramatically. But the oxygen crash likely played a significant role. Organisms adapted to 30% oxygen couldn't function at 15%. The giant insects vanished. Many plant species died out. Ecosystems restructured completely. Lightning frequency during this transition period would have been chaotic. As oxygen dropped, the atmosphere's electrical properties changed. Storm intensity fluctuated wildly. The global electrical circuit that had maintained relatively stable patterns for millions of years suddenly destabilized. This disruption affected nitrogen deposition, fire frequency, and atmospheric chemistry feedback loops. The survivors that emerged from the Permian extinction inherited a radically different electrical environment. Atmospheric composition had fundamentally altered the way storms formed and electricity moved through the air. Lightning didn't just become less frequent. It changed character entirely. Lower oxygen meant lower electrical conductivity. The atmosphere became more resistant to charge separation. Storm clouds still formed, but the electrical potential required to trigger a discharge increased. Lightning strikes occurred less often, but carried different energy profiles. The channels themselves behaved differently in the thinner oxygen-depleted air. This created unexpected consequences for nitrogen cycling. Remember that lightning produces nitrogen oxides by ionizing atmospheric nitrogen. These compounds fall to Earth in rain, fertilizing plant growth. With fewer lightning strikes, less nitrogen entered the biosphere through atmospheric deposition. Plants adapted to nitrogen-rich environments suddenly faced scarcity. Some species couldn't adjust. Others evolved relationships with nitrogen-fixing bacteria, forming symbiotic partnerships that compensated for reduced atmospheric input. The Triassic period that followed saw Earth slowly recovering. Volcanic activity continued pumping CO2 into the atmosphere. Temperatures rose again. New plant species evolved, gradually increasing oxygen production. But the atmospheric chemistry never quite returned to Carboniferous levels. Earth had shifted to a new equilibrium, one that persists in modified form today. Lightning frequency during the Triassic stabilized at levels perhaps 3 times modern rates. Still dramatic compared to our current 560 million annual strikes, but nowhere near the billions of flashes that lit Carboniferous skies. Storm patterns became more predictable. The chaotic electrical feedback loops that characterized earlier periods gave way to more stable atmospheric circulation. Then came another shift. The Jurassic period brought renewed volcanic activity and rising CO2 levels. Temperatures climbed again. Oxygen levels increased modestly, reaching perhaps 25%. Lightning frequency responded accordingly, ticking upward as atmospheric conditions favored more intense convection. But something else was happening during this time. Continental drift had broken apart Pangaea, the supercontinent that dominated the Permian. As landmasses separated, ocean circulation patterns changed. New ocean currents redistributed heat differently across the planet. Climate zones became more distinct. Tropical regions grew wetter, while interior continental areas remained arid. These geographical changes affected lightning distribution rather than just frequency. Coastal regions experienced more thunderstorms as moist ocean air collided with land. Interior deserts saw fewer storms despite favorable atmospheric chemistry. Lightning became geographically concentrated in ways that hadn't occurred during earlier periods when land masses were arranged differently. The Cretaceous period represents another peak in ancient lightning activity. Oxygen levels climbed back toward 30%. Global temperatures soared, sea levels rose dramatically, creating vast, shallow seas that pumped moisture into the atmosphere. The combination proved ideal for thunderstorm formation. Fossil charcoal from Cretaceous deposits appears in abundance, suggesting frequent wildfires ignited by lightning. Some paleobotanists argue that fire became such a regular feature of the landscape that plant communities adapted specifically to burn. Certain species evolved thick bark for fire protection. Others developed seeds that germinated only after exposure to high temperatures. Fire ecology, driven largely by lightning ignition, shaped vegetation patterns across entire continents. Volcanic lightning added another layer during this period. The Cretaceous saw intense volcanic activity, particularly around the Pacific Ring of Fire. Eruptions weren't just occasional events. They occurred with startling frequency, some lasting for thousands of years. Each major eruption generated its own electrical storms. These volcanic lightning displays differed fundamentally from meteorological lightning. When volcanic ash particles collide within an eruption column, they generate static electricity through friction. The electrical field builds rapidly, discharging in brilliant flashes that illuminate the ash cloud from within. Modern observations of volcanic lightning show discharge rates exceeding anything seen in normal thunderstorms. The 2022 eruption of Hunga volcano in Tonga produced nearly 200,000 lightning flashes throughout the event. At peak intensity, the volcanic plume generated 2,600 flashes per minute. Lightning occurred at altitudes exceeding 30 kilometers, far higher than typical thunderstorm activity. This single modern eruption offers a glimpse into what Cretaceous skies might have looked like during major volcanic episodes. Ancient volcanic lightning occurred much closer to ground level than its modern counterpart. Early Earth's volcanic plumes contained additional reducing gases that enhanced electrical discharge. Research shows that volcanic lightning during Earth's early history produced hydrogen cyanide concentrations an order of magnitude larger than general lightning. These compounds played crucial roles in prebiotic chemistry, potentially contributing to the origin of life itself. The connection between lightning and life's origins deserves attention. The famous Miller-Urey experiment demonstrated that electrical discharges through primitive atmospheric gases could produce amino acids and other organic compounds. Using a mixture of water, methane, ammonia, and hydrogen, researchers replicated lightning effects with electrodes. 15% of the carbon formed organic compounds. 2% became amino acids. Scale this up to billions of lightning strikes annually on early Earth, and the production of prebiotic compounds becomes staggering. Lightning essentially functioned as a planetary chemistry lab, synthesizing complex organic molecules from simple atmospheric gases. Some of these compounds washed into ancient oceans, concentrating in tidal pools where further reactions occurred. But lightning's contribution to early life extended beyond organic synthesis. Those billions of ground strikes produced another crucial resource: phosphorus. When lightning hits soil, it generates temperatures exceeding 3,000 degrees Celsius. At these temperatures, lightning fuses soil particles into glassy tubes called fulgurites. Fulgurites aren't just geological curiosities. They represent permanent records of ancient lightning strikes. When researchers examine fulgurite composition, they find phosphorus released from minerals that normally lock it away. This bioavailable phosphorus, essential for DNA, RNA, and cellular energy systems, becomes accessible to primitive organisms only through lightning's violent transformation of soil chemistry. Early Earth's intense lightning activity could have generated enormous quantities of bioavailable phosphorus. Some researchers estimate that lightning-produced phosphorus exceeded all other sources combined during certain periods. Without this lightning-generated nutrient supply, early life might have remained phosphorus-limited, unable to develop the complex biochemistry that eventually led to modern organisms. Fulgurites themselves offer windows into ancient atmospheric conditions. Gases trapped within fulgurite bubbles preserve atmospheric composition at the moment of formation. CO2 concentrations, oxygen levels, even temperature proxies can be extracted from these tiny glass capsules. Some fulgurites contain gases trapped for hundreds of millions of years, providing direct samples of ancient atmospheres. The oldest confirmed fulgurite dates to the Permian period, though older specimens likely exist undiscovered. These ancient lightning fossils appear in sedimentary layers worldwide, their distribution mapping ancient storm patterns. High concentrations in certain geological formations suggest regional lightning hotspots where atmospheric conditions favored intense electrical activity. Paleolightning research combines fulgurite evidence with another indicator: lightning-induced remanent magnetization. When lightning strikes rock, the intense magnetic field temporarily realigns magnetic minerals. This realignment freezes into place as the rock cools, creating a permanent magnetic signature. By mapping these signatures across ancient rock formations, researchers reconstruct lightning strike density over geological timescales. This technique revealed surprising patterns. Lightning concentration varied dramatically across ancient landscapes. Mountainous regions showed elevated strike density, consistent with modern observations that high elevation promotes thunderstorm formation. But some lowland areas also showed intense lightning activity during periods of extreme atmospheric instability. The Cretaceous-Paleogene boundary, marking the asteroid impact that killed the dinosaurs 66 million years ago, shows unusual lightning signatures. The impact itself generated enormous electrical discharges as vaporized rock and ejected debris created a global dust cloud. But the years following the impact saw lightning frequency crash as atmospheric particulates blocked sunlight, cooling the planet and suppressing convection. This post-impact lightning drought had cascading effects. Reduced nitrogen deposition stressed surviving plant communities. Fire frequency dropped dramatically. The nitrogen cycle, dependent on lightning-produced compounds, nearly collapsed. Recovery took thousands of years as atmospheric clearing gradually restored normal storm patterns. Throughout the Cenozoic era that followed, lightning frequency continued declining toward modern levels. Oxygen stabilized around 21%. CO2 concentrations dropped as plant communities recovered and carbon burial resumed. Global temperatures cooled toward present values. The extreme electrical activity that characterized earlier periods faded into geological memory. But even during the Cenozoic, lightning remained more common than today. The Eocene epoch, roughly 50 million years ago, saw temperatures significantly warmer than present. Arctic regions supported subtropical vegetation. Palm trees grew in Alaska. Under these hothouse conditions, thunderstorms occurred more frequently across broader latitudes. Ice core data from Antarctica contains evidence of this enhanced lightning activity. Nitrate concentrations in ancient ice layers correlate with atmospheric temperature. Warmer periods show elevated nitrates, indicating increased lightning-produced nitrogen deposition. This creates a proxy record of lightning frequency extending back millions of years. The gradual cooling into the current Ice Age epoch reduced lightning frequency further. As ice sheets advanced from the poles, global temperature gradients steepened. Storm tracks shifted toward lower latitudes. Polar regions, once electrically active during warmer periods, became lightning-free zones. Modern lightning distribution reflects this Ice Age configuration. Most strikes occur in tropical regions, where warm, moist air favors convection. Temperate zones experience seasonal lightning activity. Polar regions see virtually no lightning. This geographical concentration differs markedly from ancient patterns, when higher global temperatures spread thunderstorm activity more evenly across latitudes. Yet even our current 560 million annual lightning strikes represent enormous energy transfer. Each discharge releases energy equivalent to several tons of TNT. Lightning heats atmospheric channels to 30,000 degrees Celsius, 5 times hotter than the sun's surface. Thunder results from explosive expansion of superheated air. This energy drives important atmospheric chemistry. Lightning-produced nitrogen oxides still contribute significantly to the global nitrogen budget. Some studies suggest lightning remains the largest natural source of atmospheric nitrogen fixation, exceeding even fossil fuel combustion. Between 1,500 and 2,000 thunderstorms must occur simultaneously worldwide to maintain Earth's global electrical circuit. This electrical circuit represents a fundamental atmospheric process. Fair weather regions show a weak electrical field pointing toward Earth's surface. This field results from thunderstorms acting as generators, pumping positive charge into the upper atmosphere, while negative charge accumulates at the surface. Lightning provides the return path, completing the circuit. Ancient Earth's electrical circuit operated on entirely different scales. With billions of lightning strikes annually, the global electrical field would have been orders of magnitude stronger. Organisms living under these conditions experience constant electromagnetic exposure. Some researchers speculate this intense electrical environment influenced early evolution, perhaps affecting mutation rates or selecting for electrical sensitivity. The atmosphere itself behaved differently under such intense electrical activity. Continuous lightning production of nitrogen oxides would have maintained elevated concentrations of these compounds. Atmospheric chemistry operated in a regime with no modern analogue. Reaction pathways that barely function today would have dominated ancient skies. Understanding these ancient electrical conditions requires integrating multiple lines of evidence. Geochemical proxies for atmospheric composition provide the foundation. Charcoal deposits indicate fire frequency. Fulgurite distribution maps lightning strike density. Paleomagnetic signatures reveal temporal patterns. Together, these independent datasets converge on a consistent picture of dramatically enhanced lightning activity throughout much of Earth's history. Human civilization developed during an unusual period of atmospheric stability. The past 10,000 years have seen relatively constant temperature, oxygen, and CO2 levels. Lightning frequency has remained stable within this narrow range. We treat current conditions as normal, but geological perspective reveals them as anomalous. For most of Earth's history, the atmosphere existed in more extreme states that generated far more frequent lightning. Climate change may be pushing us back toward those ancient conditions. Rising CO2 levels increase global temperatures. Warmer temperatures enhance convection. More intense convection generates more thunderstorms. Early research suggests lightning frequency has already increased over recent decades, though the signal remains noisy and uncertain. Future projections indicate continued increases. Some climate models predict lightning frequency could double by 2100 under high-emission scenarios. This wouldn't approach Carboniferous levels, but it represents a significant shift from the stable electrical environment humanity has known. The ancient past may be offering a preview of Earth's electrical future. Studying ancient lightning demands detective work across geology, chemistry, and physics. No direct observations exist. No ancient weather stations recorded storm frequency. Instead, scientists piece together evidence from rocks, sediments, and atmospheric proxies. Each clue offers a fragment of the electrical story written into Earth's geological record. Fulgurites provide the most direct evidence. When lightning strikes sand or soil, it releases over 100 million volts into the ground. This enormous energy vaporizes and melts silica-rich material instantly. Within 1 second, the superheated channel solidifies into glassy tubes, crusts, and branching structures. These formations capture the exact moment of discharge, preserving it for millions of years. Finding fulgurites requires patience and luck. They form irregularly, scattered across ancient landscapes now buried beneath sediment layers. Paleontologists occasionally stumble across them while searching for fossils. Geologists mapping rock formations recognize their distinctive appearance. Each discovery represents one lightning strike frozen in time, a single data point in reconstructing ancient storm patterns. The density of fulgurites in a given rock layer suggests local lightning frequency. Abundant fulgurites indicate regions experiencing frequent strikes. Sparse fulgurites suggest fewer storms. By mapping fulgurite distribution across different geological periods, researchers build spatial pictures of where lightning concentrated millions of years ago. Dating fulgurites presents technical challenges. The glass itself forms too quickly to incorporate useful radiometric markers. Instead, scientists date the surrounding rock layers. Fossiliferous rocks above and below provide age brackets. The oldest confirmed fulgurite dates to the Permian period, though older specimens likely await discovery in deeper, less explored formations. Gas bubbles trapped within fulgurite glass offer additional information. Carbon dioxide, nitrogen, and other atmospheric gases get sealed inside during formation. These tiny time capsules preserve samples of ancient air. Analyzing their composition reveals atmospheric conditions at the moment of lightning strike. CO2 concentrations hint at paleoclimate. Nitrogen isotopes suggest biological activity. Each bubble contains chemical signatures of the ancient world. Charcoal deposits complement fulgurite evidence. Extensive charcoal layers indicate widespread wildfires. Since lightning triggers most natural fires, abundant charcoal correlates with high lightning frequency. The Carboniferous period shows particularly rich charcoal deposits, preserved in coal seams and sedimentary rocks worldwide. Fusane, fossilized charcoal found in coal, appears widely in Carboniferous deposits. Early geologists dismissed it as contamination or unusual plant material. Modern analysis confirms it represents charcoal, the direct product of wildfire. Its abundance throughout Carboniferous coal suggests fire was not occasional but constant, a fundamental ecological force shaping ancient forests. The occurrence of fire depends on multiple factors. Atmospheric oxygen must exceed 16% for combustion to propagate. At modern levels around 21%, fires ignite and spread readily. Above 23%, even damp vegetation burns freely. The Carboniferous atmosphere, containing 25 to 35% oxygen, existed in this hyperflammable state for tens of millions of years. Lightning provided ignition in this oxygen-rich world. Volcanic eruptions contributed some fires, as did meteorite impacts and spontaneous combustion. But lightning remains the most prevalent natural fire trigger across all time periods. The correlation between extensive charcoal deposits and elevated oxygen levels strongly suggests lightning frequency increased proportionally. Charcoal preservation requires specific conditions. Fires must burn intensely enough to create charcoal, yet remain incomplete, so unburned material survives. Rapid burial in sediment protects charcoal from oxidation and decay. Swamps and wetlands provide ideal preservation environments. The Carboniferous landscape, dominated by vast coastal swamps, offered perfect conditions for preserving fire evidence. By the late Carboniferous, charcoal appears common or abundant across multiple rock types. Tropical wetland peats contain it. Nearshore sediments preserve it. Even deeper marine deposits show traces, carried offshore by rivers and wind. This widespread distribution indicates wildfire was not localized but global, affecting ecosystems across ancient continents. Wildfire shaped Carboniferous ecology profoundly. Frequent burns prevented any single plant species from dominating. Fire-adapted plants evolved strategies for surviving and exploiting post-fire conditions. Some developed thick bark. Others stored energy underground. regrowing quickly after flames passed. The fossil record shows clear evidence of fire-adapted characteristics appearing and diversifying during this period. The nitrogen cycle also bears lightning's signature. Modern lightning produces between 1 and 20 teragrams of nitrogen oxides annually. These compounds form when lightning channels ionize atmospheric nitrogen. The extreme heat breaks apart stable nitrogen molecules, allowing them to react with oxygen. The resulting nitrogen oxides dissolve in rainwater, eventually reaching soil where plants absorb them. Ancient lightning would have generated proportionally more nitrogen oxides. With 5 to 10 times current lightning frequency, nitrogen fixation rates would have exceeded modern levels substantially. This enhanced nutrient input likely influenced plant productivity and ecosystem structure. The lush Carboniferous forests, growing with unprecedented vigor, may have benefited from lightning-supplied nitrogen. Paleomagnetic signatures offer another line of evidence. Lightning generates powerful electromagnetic pulses. These pulses can remagnetize rocks and minerals near the strike point. The resulting magnetic anomalies differ from normal geological magnetization. They appear as localized distortions in otherwise uniform magnetic fields. Identifying lightning-induced magnetization requires careful measurement. Researchers must distinguish it from other sources of magnetic anomalies. Volcanic activity, meteor impacts, and even human activity create similar signatures. Only through detailed analysis of magnetic field patterns, combined with geological context, can scientists confidently attribute anomalies to ancient lightning. This technique works best in areas with minimal subsequent disturbance. Regions experiencing intense geological activity after lightning strikes tend to overprint or erase the original magnetic signature. Stable continental interiors preserve lightning magnetization better than tectonically active zones. Careful site selection improves detection success rates. Atmospheric chemistry models provide theoretical frameworks for interpreting physical evidence. By reconstructing ancient atmospheric composition from geological proxies, scientists can estimate thunderstorm frequency. Carbon dioxide levels derived from paleosols indicate temperature. Temperature controls atmospheric instability. Greater instability produces more thunderstorms. These models incorporate multiple variables. Solar radiation levels changed as the sun aged. Continental positions affected heat distribution. Ocean currents redistributed thermal energy. Vegetation cover influenced water cycling. Each factor contributed to the atmospheric conditions that generated lightning. Early Carboniferous temperatures averaged around 20 degrees Celsius, warmer than today. Carbon dioxide concentrations reached approximately 1,500 parts per million, 4 times current levels. This greenhouse effect created a hot, humid world prone to intense convection. Thunderstorms would have formed frequently across tropical and temperate latitudes. By the Middle Carboniferous, cooling had begun. Atmospheric CO2 declined to about 350 parts per million near modern concentrations. Global temperatures dropped to roughly 12 degrees Celsius. This cooling resulted from carbon sequestration in vast coal swamps. Plants pulled CO2 from the atmosphere faster than geological processes could replace it. The cooling brought Earth dangerously close to global glaciation around 300 million years ago. Ice sheets expanded from the poles. Sea levels dropped. Climate became more seasonal. Yet even during this cooler period, atmospheric oxygen remained elevated. The combination of adequate moisture, high oxygen, and seasonal storms maintained substantial lightning activity. Volcanic lightning adds complexity to ancient electrical activity. Modern volcanic eruptions produce spectacular lightning displays within ash plumes. The 2022 Hunga Tonga eruption generated nearly 200,000 lightning flashes, peaking at over 2,600 strikes per minute. These rates exceed any meteorological thunderstorm ever recorded. Volcanic lightning arises from colliding ash particles. As eruption columns rise rapidly, ash fragments rub against each other, generating static electricity. The volcanic plume becomes electrically charged. When charge separation reaches critical levels, lightning discharges restore electrical balance. The process resembles thunderstorm electricity, but operates on compressed timescales and extreme scales. Ancient Earth experienced far more volcanic activity than present. Plate tectonics operated differently during some periods. Large igneous provinces erupted with unprecedented intensity. These massive volcanic episodes would have generated continuous volcanic lightning over extended periods. Combined with meteorological lightning, total electrical activity would have been staggering. Volcanic lightning occurred closer to ground level than meteorological lightning. Eruption columns often remained below 20 kilometers altitude. This proximity meant lightning produced chemicals deposited more efficiently into surface environments. Volcanic lightning contributed disproportionately to chemical processes affecting early life, despite representing smaller total discharge numbers. The Miller-Urey experiments demonstrated lightning's role in prebiotic chemistry. By simulating early Earth conditions and applying electrical discharges, researchers produced amino acids and organic compounds from simple atmospheric gases. 15% of carbon formed organic compounds. 2% became amino acids, essential building blocks for life. Ancient lightning would have conducted this experiment continuously across the entire planet. Billions of annual strikes processing atmospheric gases, coastal regions, where lightning strikes ground frequently, accumulated the highest concentrations of organic molecules. Tidal pools concentrated these compounds further. Wet-dry cycles facilitated complex chemistry. Some scientists speculate lightning was essential for life's origin. Chemical pathways leading from simple molecules to self-replicating systems require energy input. Lightning provided abundant recurring energy. Each strike created a temporary chemical reactor operating at extreme temperature and pressure. Products from countless strikes accumulated over millions of years. Phosphorus availability particularly benefited from lightning. This element limits biological productivity in many ecosystems. Lightning strikes create fulgurites, which weather slowly, releasing phosphorus into soil and water. Ancient Earth's billion-plus annual strikes would have generated massive phosphorus supplies, potentially accelerating early evolution. The transition from frequent ancient lightning to modern patterns occurred gradually. No single event reduced lightning activity. Instead, cumulative atmospheric changes over hundreds of millions of years slowly diminished electrical storm frequency. Carbon dioxide levels stabilized. Oxygen concentrations declined from Carboniferous peaks. Volcanic activity decreased as Earth cooled internally. Each change reduced lightning incrementally. Lower CO2 meant cooler temperatures and less convection. Declining oxygen altered atmospheric electrical properties. Reduced volcanism eliminated a major lightning source. By the time dinosaurs roamed Earth, lightning had decreased significantly from Carboniferous levels, though still exceeding modern frequency. The past 2 million years saw lightning stabilize near current rates. Ice Age cycles caused some variation. Glacial periods experienced fewer storms due to cooler temperatures. Interglacial warm periods saw modest increases. But overall, quaternary lightning remained within a relatively narrow range compared to the wild swings of deeper time. This stability created the electrical environment in which humanity evolved. Our ancestors experienced lightning as a powerful but manageable force, frequent enough to shape ecosystems and provide occasional ignition for controlled fire use, not so constant as to prevent civilization from developing. We inherited an atmosphere in electrical equilibrium, balanced between past extremes. Human civilization developed during this unusual stability. The Holocene epoch, spanning the last 11,700 years, represents one of the most climatically stable periods in Earth's history. Temperature, CO2, oxygen, and lightning frequency varied minimally. Agricultural societies arose, cities formed, and technology advanced under consistent atmospheric conditions. We treat this stability as normal because it encompasses all recorded history. Ancient texts describe lightning similarly to modern observations. Historical storm records, though imprecise, suggest frequencies comparable to today. The electrical environment has remained essentially constant throughout human experience, yet geological perspective reveals our normalcy as anomalous. For most of Earth's history, the atmosphere existed in more extreme states. Lightning flashed with frequencies we can barely imagine. Electrical storms of carboniferous intensity would paralyze modern civilization. Our infrastructure, designed for current conditions, could not withstand such relentless electrical assault. Climate change may be returning us toward ancient conditions. Rising CO2 levels already exceed anything experienced during human history. If emissions continue unchecked, atmospheric composition will approach states not seen since the Pliocene epoch 3 million years ago. Temperature increases will enhance convection, generating more thunderstorms. Early research suggests lightning frequency has already increased. Satellite observations show modest upward trends in some regions. The signal remains noisy, complicated by natural variability and measurement uncertainties, but the direction appears clear. Warmer atmosphere equals more lightning. Future projections reinforce this trajectory. Climate models predict lightning could increase 50 to 100% by 2100 under high emission scenarios. This doesn't approach carboniferous levels, but represents significant departure from the electrical environment humanity knows. Infrastructure designed for current lightning frequency may prove inadequate. Wildfires could increase. Power grids face greater disruption. Communication systems require hardening. The ancient past offers a preview of Earth's electrical future. As we push atmospheric composition towards states that existed millions of years ago, we should expect electrical activity to follow. Lightning shaped ancient ecosystems profoundly. It may shape our future just as powerfully. Understanding how ancient Earth managed intense electrical activity provides valuable lessons for the challenging climate ahead. Modern satellites can detect lightning anywhere on Earth. Sensors track each flash, measuring intensity, location, and frequency with precision impossible just decades ago. The worldwide Lightning Location Network monitors strikes globally in real time. This technology reveals patterns ancient scientists could only guess at. Tropical regions generate the most lightning. Central Africa, South America, and Southeast Asia flash constantly. The Congo Basin produces more electrical activity than any other location. Lakes Victoria and Maracaibo compete for the title of lightning capital. Over land, storms intensify during afternoon hours when surface heating peaks. Maritime regions show different patterns. Lightning occurs more frequently at night over oceans as temperature contrasts shift. Coastal zones experience transitional rhythms, blending land and sea influences. These modern observations provide the baseline for understanding how ancient Earth differed fundamentally from conditions we consider normal. Satellite data accumulates year after year. Researchers now possess decades of continuous lightning measurements. They've mapped seasonal variations, identified climate correlations, and detected subtle trends. One finding stands out. Lightning frequency responds quickly to temperature changes. Warmer years produce more strikes. Cooler periods show measurable decreases. The relationship isn't perfectly linear, but the connection is unmistakable. Every degree of warming translates into increased electrical activity. This correlation allows scientists to project backward. If modern temperature increases cause measurable lightning changes, past temperature extremes must have produced dramatic differences. The Carboniferous wasn't slightly warmer in some regions. It was fundamentally hotter globally, with CO2 levels quadruple modern concentrations. That heat drove convection with intensity we rarely witness today. The atmosphere churned constantly, generating thunderstorms that never ceased. Consider what satellite observations reveal about extreme weather events. When hurricanes form, lightning increases within their circulation. As tornadoes develop, electrical activity spikes dramatically. Volcanic eruptions generate lightning far exceeding normal thunderstorm intensity. These extreme events showcase what atmosphere is capable of producing when conditions align perfectly. Ancient Earth existed in perpetual extreme conditions. What we consider exceptional weather occurred routinely. The baseline shifted entirely. Modern satellites also detect lightning's electromagnetic signature from space. Each strike produces radio waves detectable thousands of miles away. This energy propagates through Earth's atmosphere, ionosphere, and magnetosphere. Scientists measure how lightning influences the entire electrical environment surrounding our planet. The discovery that lightning affects space weather opened new research avenues. Ancient lightning, occurring at much higher frequencies, would have created fundamentally different electromagnetic conditions. Earth's magnetic field interacted with constant electrical discharges, possibly influencing atmospheric chemistry in ways still being investigated. Lightning detection technology has revealed another crucial pattern. Not all regions show equal sensitivity to climate change. Some areas experience disproportionate increases in electrical activity as temperatures rise. The Arctic, traditionally quiet electrically, now generates lightning where none occurred historically. Permafrost regions experience storms as frozen ground thaws, and temperature gradients steepen. These observations suggest feedback mechanisms. As climate changes, new lightning patterns emerge. Those patterns alter ecosystems, potentially accelerating further change. Ancient Earth experienced these feedbacks continuously. The atmosphere existed in dynamic equilibrium between multiple reinforcing processes. Lightning wasn't just responding to conditions. It actively shaped them through nitrogen fixation, fire ignition, and chemical transformations. The electrical activity measured by modern satellites represents Earth in relatively stable state. Year-to-year variations exist, but they fluctuate around consistent average. Ancient Earth knew no such stability. The baseline itself shifted dramatically across geological periods. Satellite technology would have recorded lightning frequencies varying by factors of 5 or 10, depending on the epoch observed. Researchers have attempted to model ancient lightning using modern observations as foundation. They input Carboniferous atmospheric conditions into climate models designed to predict thunderstorm frequency. The results consistently show massive increases in electrical activity. Some models suggest strikes occurring 10 times more frequently. Others predict even higher multipliers. The uncertainty stems from incomplete understanding of how extreme oxygen levels affected electrical discharge. Modern atmosphere contains 21% oxygen. We understand lightning behavior under these conditions thoroughly, but at 35% oxygen, electrical properties change fundamentally. The breakdown voltage of air decreases. Sparks jump more easily. Lightning may have occurred at lower energy thresholds, creating more frequent but potentially less intense discharges. Alternatively, the energy available in oxygen-rich atmosphere might have produced more powerful strikes. The physics remains debated. What isn't debated is directionality. Every model, regardless of assumptions, predicts substantially more ancient lightning. The question isn't whether increase occurred, but its magnitude. Conservative estimates suggest doubling or tripling. Aggressive models predict tenfold increases. The truth likely falls somewhere between, varying by geological period and regional conditions. These models also reveal temporal patterns. Lightning didn't increase uniformly throughout each day. Just as modern lightning peaks in afternoon over land, ancient patterns followed circadian rhythms. But the intensity of those peaks exceeded anything modern Earth experiences. Imagine afternoon thunderstorms occurring simultaneously across every landmass. The global electrical circuit would have pulsed with energy unmatched in recent history. Nighttime wouldn't have brought complete relief. Volcanic eruptions continued regardless of solar heating. Ocean storms generated lightning continuously. The planet never fell electrically silent. Modern observations also illuminate lightning's chemical impacts. Each strike produces nitrogen oxides, fixing atmospheric nitrogen into forms usable by life. Current lightning generates between 1 and 20 teragrams of fixed nitrogen annually. This contribution rivals industrial fertilizer production. It represents crucial input into Earth's nitrogen cycle. Ancient lightning, occurring far more frequently, would have fixed nitrogen at proportionally higher rates. Some estimates suggest 50 to 100 teragrams annually during peak Carboniferous periods. This nitrogen rained down onto forests and swamps, fertilizing the very plants producing atmospheric oxygen. The feedback loop closed perfectly. More oxygen enabled more lightning. More lightning fixed more nitrogen. More nitrogen grew more plants. More plants produced more oxygen. The cycle reinforced itself until other limiting factors intervened. Satellite technology has also revealed lightning's role in atmospheric cleaning. Each discharge produces hydroxyl radicals, powerful oxidizing agents that break down methane and other greenhouse gases. Modern lightning helps regulate atmospheric chemistry, preventing methane from accumulating to dangerous levels. Ancient lightning performed this function at amplified scale. The Carboniferous atmosphere contained different chemical balances than today. Methane concentrations varied as swamps expanded and contracted. Volcanic gases introduced sulfur compounds and other reactive species. Lightning acted as atmospheric detergent, constantly scrubbing the air through chemical reactions initiated by electrical energy. Without this cleaning mechanism, atmospheric composition might have drifted towards states incompatible with complex life. Lightning maintained breathable air through relentless chemical transformation. The question arises whether ancient organisms adapted specifically to high lightning frequency. Modern trees show clear adaptations. Tall species develop deep root systems that ground electrical charge safely. Bark characteristics influence strike survival. Some species thrive in frequently burned environments, their seeds requiring fire for germination. These adaptations evolved under modern lightning regimes. Ancient plants faced far more intense electrical pressure. Fossil evidence suggests Carboniferous trees possessed different structural characteristics than modern species. Their bark was thicker. Their root systems spread differently. Whether these features represented lightning adaptations remains speculative, but the selective pressure certainly existed. Any tree unable to withstand frequent strikes would be eliminated rapidly. Over millions of years, forests evolved alongside the electrical environment, each shaping the other. Animal adaptations are harder to detect in fossil record. Modern animals show behavioral responses to lightning. They seek shelter before storms arrive, sensing electromagnetic changes. They avoid tall trees and open ground during electrical activity. Whether ancient animals possess similar instincts is unknown, but the evolutionary pressure was immense. Any species failing to avoid lightning would suffer higher mortality. Behaviors that minimize strike risk would be strongly selected. The fossil record preserves occasional direct evidence of lightning strikes. Fulgurites, as mentioned earlier, form when lightning hits sandy soil. These glassy tubes preserve the moment of impact. Some fulgurites contain organic material, suggesting the strike hit near vegetation or even animals. A few specimens show fossilized root systems encased in glass, frozen at the instant lightning traveled through soil. These rare finds provide glimpses into ancient lightning's immediate effects. Dating fulgurites reveals temporal patterns in lightning frequency. Layers containing numerous fulgurites indicate periods of intense electrical activity. Layers with few specimens suggest quieter intervals. This geological record, though incomplete, corroborates atmospheric models. The Carboniferous shows abundant fulgurites. The Permian contains fewer. Later periods show further declines. The physical evidence aligns with theoretical predictions based on atmospheric composition. One surprising finding emerged from fulgurite studies. Ancient lightning sometimes struck the same location repeatedly. Some formations show multiple fulgurite tubes intersecting, created by separate strikes hitting nearly identical spots. This pattern suggests certain geographic features attracted lightning preferentially. Hilltops, isolated trees, and mineral deposits with high iron content would have been struck far more often than surrounding areas. These lightning hotspots experienced environmental conditions unlike anywhere else on ancient Earth. The energy released by ancient lightning also deserves consideration. Modern lightning discharges typically carry between 1 and 5 billion joules of energy. Cloud-to-ground strikes release approximately 1/3 of this energy into Earth. The remainder dissipates in the atmosphere. Ancient lightning occurring in different atmospheric conditions may have carried different energy levels. Oxygen-rich air conducts electricity differently than modern atmosphere. The electrical resistance changes. This affects how energy distributes between atmosphere and ground. Some researchers suggest ancient strikes delivered more energy to Earth's surface, creating more intense fulgurites and starting larger fires. Others argue the increased oxygen allowed more frequent but less energetic discharges. The debate continues. What we can say with certainty is that total electrical energy dissipated by ancient lightning far exceeded modern levels. Even if individual strikes carried identical energy, 10 times the frequency means 10 times the total energy release. This energy didn't disappear. It transformed into heat, light, chemical bonds, and mechanical shock waves. Ancient Earth's energy budget included a massive electrical component, absent from modern calculations. That energy drove processes we're only beginning to understand. It may have influenced atmospheric circulation patterns, creating electrical effects on global weather systems. It certainly affected the ionosphere, the electrically charged layer of atmosphere where lightning energy propagates. Ancient ionospheric conditions would have differed dramatically from today's, potentially affecting how radio waves propagated and how cosmic radiation penetrated to Earth's surface. These considerations matter for understanding ancient life. Cosmic radiation influences mutation rates. If ancient ionospheric conditions provided different shielding, mutation rates might have varied accordingly. Evolution itself could have proceeded at different speeds, driven partly by electrical factors. The speculation extends to consciousness and behavior. Some researchers propose that electromagnetic fields affect animal cognition. If ancient Earth possessed fundamentally different electromagnetic environment due to constant lightning, perhaps animal behavior and even evolution of nervous systems followed different trajectories. The evidence for such effects remains circumstantial, but the questions are legitimate. Lightning shaped ancient Earth in ways extending far beyond simple fire ignition and nitrogen fixation. Modern satellite observations have revealed one more crucial pattern. Lightning doesn't just respond to climate, it influences it. The nitrogen oxides produced by lightning affect atmospheric chemistry, influencing greenhouse gas concentrations and ozone levels. The fire's lightning ignites released carbon dioxide and particulates that affect temperature and precipitation. Lightning creates feedback loops between electrical activity and climate conditions. These feedbacks operate on modern Earth, though their magnitude is modest. On ancient Earth, with vastly more lightning, these feedbacks would have been correspondingly stronger. Lightning wasn't just byproduct of ancient climate. It was active participant in regulating atmospheric composition and global temperature. The system was self-modulating, with lightning acting as both sensor and actuator in Earth's climate control system. Understanding these ancient patterns matters because Earth may be returning towards similar conditions. Not completely. We won't reach carboniferous oxygen levels or volcanic activity. But CO2 concentrations are rising toward levels not seen for millions of years. As they climb, lightning frequency follows. The feedback loops that operated in deep time are reactivating. We're conducting a planetary experiment, pushing atmospheric composition toward ancient states without fully understanding the consequences. Lightning will increase. That much is certain. How much it increases and what cascading effects follow remains to be seen. The ancient past offers warnings we should heed carefully. The geological record preserves one particularly dramatic example of these dynamics. Around 252 million years ago, at the boundary between the Permian and Triassic periods, Earth experienced its most catastrophic mass extinction. Over 90% of marine species vanished. 70% of terrestrial vertebrates died out. The planet nearly lost complex multicellular life entirely. What caused this near-total collapse? The answer involves lightning, though not as direct cause. Massive volcanic eruptions in what's now Siberia released stupendous quantities of carbon dioxide and other gases. These eruptions continued for hundreds of thousands of years, fundamentally altering atmospheric composition. CO2 concentrations spiked. Global temperatures soared. Ocean chemistry shifted toward acidic conditions incompatible with shell-building organisms. Lightning frequency would have increased dramatically during this crisis. Higher CO2 meant higher temperatures. Higher temperatures meant more vigorous convection and more thunderstorms. The dying Earth crackled with electrical fury, even as ecosystems collapsed beneath unrelenting environmental stress. But lightning played another role during this crisis, one researchers are only beginning to understand. The massive fires ignited by increased lightning strikes released additional carbon dioxide, creating positive feedback. More CO2 meant more lightning meant more fires meant more CO2. The system spiraled toward catastrophe. Some scientists propose that lightning-induced nitrogen oxides contributed to atmospheric chemistry changes that damaged the ozone layer. Without adequate ozone protection, harmful ultraviolet radiation reached Earth's surface at elevated levels, stressing already struggling ecosystems. Lightning wasn't the primary killer, but it may have been an accomplice, amplifying other destructive processes. The recovery from this extinction took millions of years. Ecosystems rebuilt themselves slowly, species by species, niche by niche. Throughout this recovery period, atmospheric conditions gradually stabilized. CO2 levels declined as volcanic activity diminished. Temperatures moderated. Lightning frequency decreased accordingly. This pattern, catastrophic disturbance followed by slow recovery, characterizes Earth's history. The planet oscillates between stable periods and crisis moments. Lightning tracks these oscillations faithfully, increasing during disruptions and decreasing during stability. It serves as both indicator and participant in planetary scale changes. Fast forward to more recent geological time, the Cretaceous period, from roughly 145 to 66 million years ago, saw another episode of elevated lightning activity. Oxygen levels during much of the Cretaceous exceeded modern values, reaching perhaps 25 to 28%. This oxygen-rich atmosphere supported the largest land animals ever to exist, the sauropod dinosaurs. These creatures defied modern biological expectations. Some weighed over 70 tons. Their necks stretched 15 meters. They consumed vegetation at rates that would strip modern landscapes bare within days. How did Earth's ecosystem support such gigantism? Elevated oxygen helped. Higher oxygen concentrations mean more efficient respiration. Animals can grow larger without hitting metabolic limitations. But the oxygen-rich atmosphere also meant more lightning. Cretaceous landscapes experienced electrical storms of intensity we can barely imagine. The fires these storms ignited would have been spectacular and terrifying. With oxygen concentrations approaching 30%, even damp vegetation burned readily. Forests that today would resist fire became tinderboxes. Lightning strikes that might produce small fires under modern conditions instead triggered infernos. Yet Cretaceous ecosystems thrived despite, or perhaps because of, these intense fires. Fire created openings in dense forests, allowing new growth. It recycled nutrients locked in dead vegetation. It maintained grasslands and savannas that might otherwise have been overtaken by trees. Dinosaurs evolved in landscapes shaped by constant burning. Some researchers propose that certain dinosaur behaviors evolved specifically as fire adaptations. Large body size provided protection from flames. Bigger animals can move through fire zones more safely. Long necks allowed browsing above smoke and heat. Migration patterns may have tracked seasonal fire regimes. The evidence for Cretaceous fires is abundant. Charcoal appears throughout geological formations from this period. Some fossil sites preserve burned vegetation still in growth position, frozen in time at the moment of combustion. The landscapes of the dinosaur age were landscapes of fire, and fire meant lightning. This relationship between oxygen, lightning, and megafauna raises intriguing questions about causation. Did high oxygen permit large animals, which then maintained conditions favorable for high oxygen? Or did high oxygen drive evolutionary pressures that favored gigantism? The answer likely involves complex feedbacks where each factor influenced others in continuous cycles. What's certain is that when oxygen levels eventually declined, the age of giants ended. By the time mammals inherited Earth, after the dinosaur extinction, oxygen had dropped closer to modern levels. Lightning frequency decreased accordingly. The electrical intensity of Earth's atmosphere diminished, and with it went some of the conditions that had permitted biological extremes. Modern researchers study these ancient patterns not just from academic curiosity, but from practical concern. Understanding how Earth's atmosphere responded to changes in the past helps predict how it will respond to changes we're imposing now. The CO2 we're adding to the atmosphere is pushing conditions towards states not seen for millions of years. One particularly concerning parallel involves the rate of change. During most natural transitions between climate states, CO2 concentrations shifted over tens or hundreds of thousands of years. Life had time to adapt. Ecosystems could migrate. Evolution operated fast enough to track environmental changes. We're changing atmospheric composition in centuries, not millennia. This pace of change is unprecedented in recent geological history. Only during catastrophic events like the Permian-Triassic extinction do we see comparable rates of atmospheric transformation. And those events caused mass extinctions. Lightning frequency is already increasing. Satellite observations show clear trends over the past few decades. As global temperatures rise, thunderstorm frequency and intensity increase. The pattern matches predictions based on ancient climate records. We're moving backward through geological time, toward atmospheric states our species never experienced. The implications extend beyond simple lightning counts. Increased electrical activity means more fires, though human fire suppression complicates this relationship. It means more nitrogen oxides entering the atmosphere, with consequences for air quality and ozone chemistry. It means more energy dissipating through atmospheric electrical circuits, potentially affecting everything from cloud formation to radio wave propagation. Some climate models predict that tropical regions will experience the largest increases in lightning frequency. These areas already host the majority of Earth's thunderstorm activity. The intensification of electrical activity in tropical zones could affect monsoon patterns, which billions of people depend on for agriculture and water supply. Higher latitudes may see even more dramatic relative changes. Arctic regions currently experience minimal lightning due to cold temperatures and stable atmospheric conditions. As the Arctic warms faster than any other part of the planet, conditions become increasingly favorable for thunderstorm development. Lightning in the far north could trigger fires in tundra and boreal forests previously protected by cold and moisture. These Arctic fires would release massive quantities of carbon currently locked in permafrost and peat. The carbon release would further warm the atmosphere, creating more lightning, triggering more fires, releasing more carbon. Another positive feedback loop, similar to those that operated during ancient climate transitions. The geological record shows that such feedbacks can push Earth's climate across thresholds into dramatically different states. Once certain tipping points are passed, the system may not return to its original configuration, even if the initial forcing is removed. The planet settles into a new equilibrium, one that may persist for millions of years. Ancient lightning patterns tell us we're approaching such thresholds. The atmospheric conditions we're creating resemble those from epochs when Earth looked fundamentally different. Not identical. The continents have moved, ocean circulation patterns have changed, life itself has evolved. But the basic physics of atmospheric electricity operates according to timeless principles. Higher temperatures mean more evaporation. More evaporation means more water vapor. More water vapor means more latent heat energy available for thunderstorm formation. More thunderstorms mean more lightning. The chain of causation is straightforward and inescapable. We can measure each link in this chain. Satellite instruments track evaporation rates. Weather balloons measure atmospheric moisture. Radar networks monitor storm intensity. Lightning detection systems count electrical discharges. Every measurement confirms the trends predicted by ancient climate records. The question isn't whether lightning will increase as we continue altering atmospheric composition. It will. The questions are how much it will increase, how quickly, and what cascading consequences will follow. Those questions remain partially unanswered because we're conducting an experiment without precedent in human history. Ancient Earth offers clues, but not perfect predictions. The planet has never before experienced rapid atmospheric changes while hosting 7 billion humans, extensive agriculture, and interconnected technological systems. Previous transitions occurred in worlds without cities, power grids, or computer networks vulnerable to electromagnetic interference. Lightning strikes already cause billions of dollars in damage annually. They ignite fires, disrupt communications, damage infrastructure, and kill people. A world with significantly more lightning will face proportionally greater challenges. Some regions may become difficult to inhabit due to constant electrical storms. Agricultural systems adapted to current lightning regimes may struggle as fire frequency increases. Insurance industries will need to recalculate risk models. Power companies will face escalating costs to protect transmission systems. Air travel routes may require adjustment to avoid intensifying electrical activity. These practical concerns pale beside deeper questions about Earth system stability. Lightning doesn't just respond to climate change. It participates in climate regulation through multiple pathways. Nitrogen oxide production affects greenhouse gas concentrations. Fire ignition influences carbon cycling. Ozone chemistry responds to electrical discharges. The feedbacks operate in complex, non-linear ways. Understanding ancient lightning helps us map these feedback loops. Each geological period provides a natural experiment showing how Earth's electrical system responds to specific atmospheric conditions. The Carboniferous teaches about oxygen effects. The Permian-Triassic boundary demonstrates crisis dynamics. The Cretaceous reveals consequences of sustained elevated conditions. By studying these ancient analogues, researchers build models of how modern climate change will unfold. The models aren't perfect. Earth's current configuration differs from any ancient state, but the fundamental processes remain constant. Physics operates identically whether applied to ancient or modern atmospheres. What emerges from this synthesis of ancient evidence and modern observation is a picture of Earth as an electrical organism. The planet generates and dissipates enormous amounts of electrical energy through atmospheric processes. This energy flow isn't incidental to climate. It's integral to how Earth maintains habitability. Lightning represents the most visible manifestation of this electrical nature, but it's just the surface expression of deeper electromagnetic processes. Earth's magnetic field, ionospheric currents, and atmospheric electric circuits form an interconnected system that influences everything from cosmic ray penetration to cloud formation. Ancient lightning patterns reveal how this system responds to perturbation. When atmospheric composition changes significantly, the electrical characteristics of the planet shift accordingly. We're witnessing such a shift now, pushed by our alteration of atmospheric chemistry. The shift will continue as long as we keep adding greenhouse gases to the atmosphere. Lightning will increase. The consequences will ripple through Earth systems in ways both predictable and surprising. Understanding these consequences requires examining specific scenarios where increased lightning would reshape human systems. Start with agriculture. Modern farming depends on predictable climate patterns. Lightning-ignited fires already burn millions of acres annually, but current agricultural practices evolved during a period of relatively stable lightning frequency. As electrical storm activity intensifies, fire regimes will shift dramatically. Consider the American Midwest. Vast cornfields and soybean crops stretch across landscapes optimized for industrial agriculture. These monocultures are vulnerable to fire in ways natural ecosystems aren't. A single lightning strike during dry conditions can ignite fast-moving blazes that consume thousands of acres before containment. As storm frequency increases, fire seasons will lengthen, insurance costs will rise. Some regions may become unviable for certain crops. Australia provides a preview. Lightning-sparked bushfires already challenge agricultural communities there. Climate change has extended fire seasons and increased electrical storm intensity. Farmers now factor lightning risk into every planting decision. They create fire breaks, install sophisticated detection systems, and maintain emergency response plans. These adaptations cost money and time. Smaller operations struggle to afford adequate protection. The forestry industry faces similar pressures. Commercial timber operations depend on decades-long growth cycles. A single catastrophic fire can wipe out investments spanning generations. As lightning frequency increases, forest fire risk calculations must adjust. Some regions may become too dangerous for commercial forestry. Others will require expensive fire suppression infrastructure that makes operations economically marginal. But food production isn't the only concern. Modern civilization runs on electricity, and electrical grids are fundamentally vulnerable to lightning. Every transmission line, transformer, and substation represents a potential strike point. Current infrastructure incorporates lightning protection, but systems designed for present conditions may prove inadequate as strike frequency doubles or triples. Power companies already spend billions protecting grid infrastructure. Lightning causes more power outages than any other weather phenomenon. Each strike can damage equipment, trigger cascading failures, and leave millions without electricity. As storms intensify, utilities face impossible choices. They can invest heavily in enhanced protection, passing costs to consumers. They can accept increased outage frequency and damaged reputation. Or they can redesign grid architecture entirely, a project requiring decades and trillions of dollars. The digital economy complicates everything. Data centers, communication networks, and financial systems depend on continuous power. Brief outages cause disproportionate disruption. A lightning strike that would have been minor inconvenience 50 years ago can now trigger cascading failures across interconnected systems. Cloud computing concentrates risk. When major data centers lose power, services worldwide suffer. Aviation represents another critical vulnerability. Commercial aircraft already navigate around thunderstorms, but increased electrical activity will congest airspace. Flight paths must avoid active storm cells. As lightning frequency rises, available routes narrow. Delays increase. Fuel consumption rises as planes detour around weather. Some routes may become uneconomical or impossible during peak storm seasons. Aircraft design incorporates lightning protection. Metal fuselages conduct electricity safely around passengers. Composite materials require special conductive layers. But protection has limits. Severe lightning can damage avionics, puncture fuel tanks, or temporarily blind pilots. As strike probability increases, safety margins shrink. Airlines may need to ground flights more frequently or invest in enhanced shielding. The space industry faces unique challenges. Rocket launches require clear weather windows. Lightning within miles of launch pads can trigger aborts. The Apollo 12 mission was struck twice during ascent. Modern launch protocols incorporate stricter weather restrictions. As electrical storm frequency increases, launch windows narrow. Space operations become more expensive and less predictable. Satellites in low orbit already encounter electrical effects. The ionosphere becomes turbulent during major storms. Increased lightning activity will intensify these disturbances. Communication satellites, GPS systems, and Earth observation platforms may experience more frequent disruptions. Space weather forecasting must account for changing electrical conditions. Urban areas concentrate lightning risk. Tall buildings attract strikes. Dense infrastructure creates multiple failure points. Cities invest heavily in lightning protection, but systems designed for historical strike frequencies may prove inadequate. Building codes will need updates. Insurance requirements will tighten. Construction costs will rise. Historical architecture presents special challenges. Ancient buildings lack modern lightning protection. Cathedrals, temples, and monuments survive centuries partly through luck. As strike frequency increases, these irreplaceable structures face elevated risk. Installing protection systems on historical buildings requires careful balance between preservation and safety. Wilderness areas tell different stories. National parks, nature reserves, and remote forests lack infrastructure to fight fires. Lightning-ignited blazes burn naturally, as they have for millions of years. But surrounding human development changes the equation. Fires that once burned unchecked now threaten communities. Fire suppression becomes necessary but ecologically damaging. Fire ecology evolved with lightning. Many ecosystems depend on periodic burns for regeneration. Some pine species require fire to release seeds. Prairie grasses evolved to survive flames. These systems developed during periods of relatively stable lightning frequency. Rapid increases in electrical activity may push ecosystems beyond adaptive capacity. Consider chaparral ecosystems in California. These fire-adapted communities evolved with lightning strikes every few decades. As climate change intensifies, fire frequency increases. Some areas now burn multiple times per decade. Native plants can't recover between blazes. Invasive species colonize burned areas. Ecosystem composition shifts fundamentally. Boreal forests face similar pressures. These vast northern woodlands store enormous carbon quantities. Lightning-sparked fires release that carbon into the atmosphere, accelerating climate change. As warming continues, boreal regions become drier and more flammable. Lightning frequency increases. Fire seasons lengthen. The result is a feedback loop. Warming increases lightning. Lightning increases fires. Fires increase warming. The Arctic provides stark examples. Tundra regions historically experienced minimal lightning. Permafrost and cold temperatures prevented fires. But warming Arctic temperatures are changing everything. Lightning strikes in far northern regions have increased dramatically. Tundra fires, once virtually unknown, now burn regularly. These fires release methane and carbon dioxide from thawing permafrost, further accelerating warming. Ocean storms present different dynamics. Lightning over water seems less dangerous. No forests to ignite, no buildings to strike. But marine lightning affects shipping, fishing, and offshore infrastructure. Oil platforms, wind farms, and undersea cables all face lightning exposure. As storm intensity increases over warming oceans, marine industries, must adapt. Lightning chemistry matters here. Strikes over oceans produce different nitrogen compounds than land strikes. Marine lightning affects phytoplankton productivity through nitrogen deposition. Changes in ocean lightning patterns could influence marine food webs. The connections remain poorly understood, but preliminary evidence suggests significant effects. Tropical regions will experience disproportionate impacts. Equatorial areas already host most lightning activity. As warming intensifies, tropical thunderstorms will become more frequent and severe. Nations near the equator face the greatest increases in electrical storm activity. Many of these countries have limited resources to adapt. Indonesia provides examples. This tropical nation experiences among the highest lightning frequencies globally. Climate change is intensifying monsoon patterns, driving more violent thunderstorms. Lightning-sparked fires threaten rainforests during dry seasons. The 2019 fires burned millions of acres, releasing enormous carbon quantities. As electrical activity increases, such disasters will become more common. Central Africa faces similar challenges. The Congo Basin experiences intense lightning activity. This region hosts the world's second-largest rainforest. Lightning-ignited fires during drought years damage ecosystems crucial for global climate regulation. As storm patterns shift, fire risk increases. Limited firefighting infrastructure makes containment difficult. South America's Amazon basin represents another critical region. Lightning frequency there is already high. Deforestation and climate change are creating drier conditions. The combination of increased lightning and reduced moisture creates catastrophic fire risk. Major Amazon fires in recent years demonstrate the vulnerability. As electrical activity intensifies, the Amazon faces potential transformation from rainforest to savanna. These regional variations matter because lightning effects aren't uniform. Some areas will experience modest increases, others will see dramatic shifts. The distribution of impacts affects global systems. If lightning increases concentrate in tropical forests, carbon cycle disruptions could be severe. If increases concentrate over oceans, marine ecosystem effects dominate. Understanding these spatial patterns requires sophisticated modeling. Climate scientists run simulations incorporating atmospheric chemistry, ocean temperatures, vegetation changes, and electrical physics. The models show consistent trends but significant regional variation. Some tropical zones could see lightning frequency double within decades. Some temperate regions may experience more modest increases. Seasonal patterns will shift as well. Lightning currently peaks during summer months in most regions. Climate change is extending warm seasons and intensifying heat. Lightning seasons will lengthen. Regions experiencing year-round electrical activity will expand. Areas with distinct wet and dry seasons may see those patterns disrupted. These temporal shifts compound adaptation challenges. Infrastructure designed for seasonal lightning exposure may face year-round risk. Fire management agencies accustomed to defined fire seasons will need to maintain readiness continuously. Agricultural calendars built around predictable weather will require adjustment. Human health effects add another dimension. Lightning directly kills more people annually than hurricanes or tornadoes in many regions. As strike frequency increases, fatalities will rise proportionally unless protective measures improve. Developing nations with limited lightning protection infrastructure face greatest risk. Indirect health effects matter too. Increased wildfire smoke affects air quality over vast areas. Respiratory illnesses increase during fire seasons. Cardiovascular problems worsen. The 2020 wildfire season in Western North America demonstrated these effects. Smoke blanketed cities thousands of miles from active fires. Hospital admissions spiked. As lightning-sparked fires become more frequent, these health impacts will intensify. Mental health consequences deserve attention. Communities repeatedly threatened by lightning-sparked fires experience chronic stress. Anxiety disorders increase. Post-traumatic stress affects survivors. The psychological burden of living in high-fire risk areas takes cumulative toll. Economic costs scale with all these impacts. Current estimates suggest lightning causes tens of billions in annual damages globally. As strike frequency increases, costs will rise proportionally at minimum. Non-linear effects could drive costs much higher. A doubling of lightning might triple damages if it pushes systems beyond coping capacity. Insurance industries are beginning calculations. Lightning risk models must adjust for changing climate. Premiums will increase in high-risk areas. Some regions may become uninsurable. The economic geography of risk is shifting as Earth's electrical system responds to atmospheric changes. These aren't distant future concerns. Changes are occurring now, measured and documented by global monitoring networks. Lightning frequency has already increased in some regions. Fire seasons have already lengthened. The trends will accelerate as atmospheric changes continue. Understanding how atmospheric electricity connects past and future requires looking at the deeper mechanisms. Lightning doesn't just respond to temperature increases. The physics involves charge separation in clouds, which depends on updraft velocity, particle collision rates, and moisture content. Warmer atmospheres hold more water vapor. Each degree Celsius increase raises atmospheric moisture capacity by roughly 7%. More moisture means more latent heat release during condensation. That energy drives stronger updrafts. Stronger updrafts create more violent particle collisions inside clouds. More collisions generate greater charge separation. Greater charge separation produces more lightning. This cascade effect explains why lightning response to warming isn't linear. A modest temperature increase triggers disproportionate electrical activity growth. Climate models incorporating these physics show lightning increasing faster than simple temperature correlations would suggest. Some projections indicate global lightning frequency could increase 50% or more by century's end under high emission scenarios. Regional patterns complicate the picture further. Tropical zones will see the largest absolute increases because they already dominate global lightning activity. But percentage increases may be highest in mid-latitudes and high-latitude regions. Areas previously too cold for significant thunderstorm development will cross thresholds. The Arctic, currently experiencing minimal lightning, could see dramatic increases as permafrost thaws and summer temperatures rise. Ocean lightning presents another variable. Oceans cover 70% of Earth's surface, but produce only 10% of lightning strikes. Land heats faster than water, creating stronger updrafts. As ocean temperatures rise, this disparity may narrow. Marine thunderstorms could become more frequent and intense. The implications extend to hurricane formation, ocean chemistry, and marine ecosystems unprepared for electrical activity. Feedback loops add uncertainty. Lightning produces nitrogen oxides that affect atmospheric chemistry. Changes in NOx distribution could alter ozone formation, aerosol production, and cloud properties. These effects feed back into lightning generation in complex ways. Some feedbacks amplify changes, others dampen them. Current models struggle to capture all interactions. The wildfire connection illustrates cascade complexity. More lightning starts more fires. More fires release more carbon. More carbon warms the atmosphere. Warmer atmosphere produces more lightning. Each element reinforces the others. Breaking these loops requires intervention at multiple points simultaneously. Preventing fires becomes harder as ignition sources multiply. Fighting fires becomes more expensive as frequency increases. Adapting infrastructure becomes essential as risk escalates. What can be done? Adaptation strategies exist but require resources and planning. Lightning protection systems can be expanded to cover more structures and landscapes. Early warning networks can be enhanced. Fire suppression capabilities can be increased. Building codes can incorporate lightning resistance. Agricultural practices can adjust to shifting risk patterns. Each adaptation carries costs. Installing lightning protection on existing infrastructure requires massive investment. Expanding firefighting capacity demands personnel, equipment, and training. Improving early warning systems needs satellite networks and ground sensors. Updating building codes faces resistance from cost-conscious developers. The economic burden falls unevenly. Wealthy nations can afford adaptation. Developing countries struggle. International cooperation becomes crucial. Lightning and fire don't respect borders. Smoke from fires crosses continents. Atmospheric changes affect everyone. Shared monitoring networks benefit all nations. Technology transfer helps vulnerable regions. Coordinated research accelerates understanding. Yet geopolitical tensions complicate cooperation. Competition for resources overrides collaboration. Short-term interests trump long-term planning. Historical precedents offer limited guidance. Previous atmospheric changes occurred over geological timescales. Species and ecosystems adapted gradually. Human civilization didn't exist during most dramatic shifts. Current changes compress millions of years of atmospheric evolution into decades. Adaptation windows narrow. Extinction risks rise. Social systems strain under rapid transformation. The Carboniferous period saw similar electrical intensity, but different context. Plants and animals evolved over millions of years to handle high lightning frequency. Forests adapted to regular fire. Insects developed strategies for surviving electrical storms. Modern ecosystems lack that evolutionary preparation. Species face threats they haven't encountered in their existence. Adaptation requires behavioral flexibility and genetic diversity. Many populations possess neither. Urban areas concentrate vulnerability. Cities pack infrastructure, populations, and economic activity into small spaces. A single lightning strike can cascade through electrical grids. Fire in dense urban areas spreads rapidly. Emergency services become overwhelmed during severe events. The 2021 heat dome over North America demonstrated urban vulnerability. Electrical demand surged. Infrastructure failed. Fires ignited. Hundreds died. Similar events will increase as lightning frequency rises. Agriculture faces direct impacts. Lightning strikes kill livestock. Fires destroy crops. Electrical interference disrupts automated farming systems. Changing lightning patterns alter growing season timing. Farmers must adjust centuries-old practices to new realities. Small-scale farmers lack resources for rapid adaptation. Food security concerns multiply as agricultural disruption spreads. Technology offers partial solutions. Lightning detection networks now provide real-time tracking. Machine learning algorithms predict strike probability. Satellite systems monitor global electrical activity. Automated alerts warn vulnerable populations. These tools help but can't eliminate risk. Detection doesn't prevent strikes. Warnings don't stop fires. Technology reduces consequences without addressing causes. The deeper challenge involves atmospheric composition itself. Lightning responds to conditions created by greenhouse gas emissions. Reducing those emissions slows atmospheric changes. Current emission trajectories suggest continued warming for decades, even with aggressive mitigation. Committed warming means committed lightning increases. Some impacts are now unavoidable. Adaptation must proceed regardless of mitigation success. Carbon dioxide remains in the atmosphere for centuries. Emissions from past decades continue affecting climate today. Current emissions commit future generations to further changes. The lightning increases measured now reflect emissions from 20 or 30 years ago. Today's emissions will manifest in lightning patterns of 2050 and beyond. This temporal disconnect complicates policy responses. Actions taken now won't show results for decades. Political systems struggle with such delayed feedback. Economic analyses attempt quantifying costs. Current estimates range from tens to hundreds of billions annually for lightning-related damages. Future costs scale with strike frequency and vulnerability. Some models suggest damages could reach trillions cumulatively over coming decades. These figures don't capture ecosystem losses, species extinctions, or cultural heritage destruction. Economic frameworks fail to price irreplaceable losses. Insurance industries recalculate risk constantly. Actuarial models incorporate changing lightning patterns. Premiums rise in high-risk zones. Coverage limitations expand. Some areas become uninsurable for lightning damage. Market signals push development away from vulnerable regions, but population inertia resists. People stay in high-risk areas despite rising costs. Adaptation happens slowly, if at all. Looking at ancient lightning offers perspective. Earth's electrical system has varied enormously across geological time. Current changes, while dramatic on human timescales, represent minor fluctuations compared to deep history. The planet has experienced much higher lightning frequencies and survived. Ecosystems reorganized. New species emerged. Life continued. This long view provides both comfort and warning. Earth will endure. Current ecosystems may not. The real question isn't whether lightning will increase, it will. The question is how societies respond. Do we adapt proactively or react to disasters? Do we protect vulnerable populations or let them suffer? Do we preserve ecosystems or accept their transformation? These choices determine outcomes more than lightning physics itself. Current trajectory suggests reactive approach dominating. Disasters prompt temporary attention. Media coverage spikes after major fire seasons. Political promises follow. Funding increases briefly, then attention wanes. Budgets shrink. Preparation languishes until the next crisis. This cycle ensures maximum damage and minimum adaptation. Alternative approaches exist. Sustained investment in monitoring and protection reduces long-term costs. Proactive infrastructure upgrades prevent catastrophic failures. Early warning systems save lives and property. Land use planning keeps development away from high-risk areas. These strategies require sustained political will and public support. Both remain scarce. Education plays crucial roles. Public understanding of lightning risk affects behavior. Knowledge of protection methods reduces casualties. Awareness of climate connections builds support for mitigation. Yet climate literacy remains low globally. Misinformation spreads faster than science. Conspiracy theories undermine trust in monitoring data. Educational efforts face uphill battles. The story of lightning connects everything. Ancient atmospheres shaped by geology, life evolving under electrical skies, climate changes cascading through physics, modern society adapting to transformed conditions. Each chapter informs the next. Understanding the past illuminates the present. Present observations constrain future projections. Future scenarios motivate current action. What matters now is recognizing the stakes. Lightning isn't just spectacular natural phenomena. It's an integral part of Earth systems connecting atmosphere, ecosystems, and civilization. Changes in lightning frequency signal broader atmospheric transformations. Those transformations affect everyone, everywhere. Ignoring lightning changes means ignoring climate reality. Addressing them requires acknowledging uncomfortable truths about human impact on planetary systems. The ancient Earth with its billion lightning strikes per year seems alien. Yet we're moving towards something resembling those conditions. Not in atmospheric composition exactly, not in the same geological context, but in electrical intensity and ecological impact. Our actions are writing a new chapter in Earth's electrical history. That chapter will define conditions for generations. The choices made now determine whether that future is manageable or catastrophic. human input. Please continue the script, maintaining exact style and tone, ending with a proper conclusion for this 9-part series. Lightning's story is ultimately about connections we failed to see. For centuries, we treated it as isolated phenomenon, dangerous spectacle, random act of nature. Now we understand its diagnostic indicator, atmospheric thermometer, ecological force, climate messenger. Every flash carries information about the state of Earth's systems. The increase we're measuring isn't anomaly. It's symptom. Rising strike frequencies reflect atmospheric changes that touch everything: temperature, moisture, circulation patterns, chemical composition. These aren't separate issues. They're facets of one interconnected system. Lightning simply makes them visible. Each bolt illuminates what's happening to the air we breathe. Ancient Earth reminds us this has happened before, not from human activity, from geological forces, volcanic outgassing, biological revolutions, planetary impacts. Each time, lightning responded. Each time, ecosystems transformed. The difference now is speed. Previous changes unfolded over millions of years. Current changes compress into decades. Evolution can't keep pace. Adaptation becomes survival test. What we do with this knowledge defines us. We can monitor and prepare, build resilience, protect vulnerable systems, or we can pretend the patterns don't matter, ignore the warnings, react only when disasters force attention. History suggests we'll choose the harder path. Humans consistently underestimate gradual changes until they become crises, but there's still time to choose differently. The atmospheric changes driving lightning increases can be slowed, not stopped immediately, not reversed quickly, but slowed enough to allow adaptation. That requires acknowledging what the lightning is telling us. The atmosphere is changing. Earth systems are responding. The consequences will touch everyone. So the next time you see lightning, think deeper than the flash. Consider what it represents. Energy from the sun heating the surface. Moisture evaporating into unstable air. Particles colliding in violent updrafts. Charges separating across cloud layers. Electrical potential building until it must discharge. That single bolt connects ocean to atmosphere to cloud to ground. It links physics to chemistry to biology to climate. And remember those ancient skies crackling with 5 billion strikes annually. Remember the Carboniferous forests burning under constant electrical assault. Remember the fulgurites forming in ancient sands, preserving evidence of storms from 300 million years ago. We're the latest chapter in that long story. What we're doing now will be written in rock layers and atmospheric records for future geologists to discover. They'll see the chemical signatures of this century. The carbon isotopes, the oxygen ratios, the trace elements. They'll reconstruct our atmosphere's composition. They'll calculate our lightning frequencies. They'll read the charcoal layers from our fire seasons. And they'll understand exactly what we did, whether we acted in time or waited too long. That's what the science shows. That's what the data reveals. That's what the lightning is telling us, if we're willing to listen. The question isn't whether we'll see more lightning. We already are. Satellite networks track it. Ground sensors measure it. The trend line climbs steadily upward, matching every prediction climate models generated years ago. What remains uncertain is how far we'll let it go before accepting what those flashes mean. Every storm system pulsing with electrical energy is a message, not metaphorical, literal. The atmosphere is telling us its changing state, moving toward configurations it hasn't held in millions of years. Configurations our civilization never evolved to handle. We built cities assuming lightning frequencies would stay constant, designed power grids for historical strike rates, planned agriculture around familiar fire seasons. All those assumptions are breaking down in real time. The Carboniferous teaches a brutal lesson. When atmospheric oxygen climbed to 35%, the world became a tinderbox. Lightning didn't just increase, It transformed entire ecosystems through relentless fire. Plants evolved thick bark or died. Animals developed fire avoidance behaviors or went extinct. The pressure was absolute. Adapt or disappear. We're not heading toward carboniferous conditions. Our trajectory is different. But the principle holds. Push atmospheric composition beyond certain thresholds, and the planet responds dramatically. Lightning frequency is one response. Forest fire patterns are another. Ecosystem disruption follows. Agricultural collapse threatens. Infrastructure fails. These aren't separate crises. They're connected symptoms of one underlying transformation. The ancient fulgurites scattered through rock layers worldwide are proof that Earth has been here before. Proof that planetary electrical systems can operate at intensities we find hard to imagine. Those glassy tubes formed when lightning, carrying 100 million volts, melted sand into permanent records of storms, from eras when humans didn't exist. They'll outlast us too, preserving evidence of what we did to the atmosphere in the 21st century. Future geologists will dig through our rock layers. They'll find our chemical signatures, elevated carbon dioxide, altered nitrogen ratios, charcoal deposits from unprecedented fire seasons. They'll reconstruct our lightning frequencies from fulgurite density. They'll understand exactly what happened, whether we chose to act or chose to ignore the warnings crackling across every thunderstorm. The science isn't ambiguous. The physics is straightforward. Warmer atmosphere holds more moisture. More moisture creates stronger updrafts. Stronger updrafts generate more violent charge separation. More charge separation produces more lightning. Each step in that chain is measurable, observable, undeniable. The only question is how much warmer we let it get. Some impacts are already locked in. Emissions from past decades guarantee continued atmospheric changes for years ahead. Lightning will increase regardless of actions taken today. But the magnitude matters enormously. The difference between 50% increase and 100% increase determines whether societies adapt or collapse, whether ecosystems transform or crash, whether billions face manageable challenges or catastrophic disruption. The ancient past offers no comfort here. Previous atmospheric transitions caused mass extinctions. The Permian-Triassic boundary event eliminated 90% of marine species. Oxygen crashes killed organisms adapted to oxygen-rich environments. Climate disruptions triggered cascading failures across ecosystems. Those transitions unfolded over millennia. Current changes compress similar magnitude shifts into decades. Speed matters. Adaptation requires time. Time we're not allowing. Indigenous cultures understood lightning differently than modern civilization does. They saw it as sacred force, respected its power, built knowledge systems around its patterns, developed practices for living alongside electrical storms. Those traditions contain wisdom we dismissed as superstition. Now we're relearning lessons written in fulgurites and charcoal deposits. Lightning isn't background phenomenon. It's active participant in shaping the world. The nitrogen it fixes fertilizes forests. The fires it ignites maintain ecosystems. The chemistry it drives regulates atmospheric composition. Remove lightning from Earth's systems and everything changes. Increase it dramatically and everything changes differently. We're running that experiment now. The results will unfold whether we pay attention or not. Modern technology gives us capabilities ancient civilizations lacked. We can monitor every lightning strike globally, model atmospheric changes decades in advance, predict fire seasons before they arrive, design infrastructure to withstand increased electrical activity. These tools work if we use them. They fail if we ignore what they reveal. Right now, we're collecting unprecedented data while making inadequate preparations. Watching measurements climb while pretending trends will somehow reverse. They won't reverse, not without changing what's driving them. Atmospheric composition responds to emissions. Emissions respond to energy systems. Energy systems respond to policy choices. Policy choices respond to political will. Political will responds to public pressure. The chain of causation leads back to collective decisions about what kind of world we're building. Every lightning bolt offers a moment of clarity. For a fraction of a second, the channel glows brighter than the sun. In that instant, atmospheric electricity connects sky to ground in visible, undeniable display. The flash fades, the thunder rolls, the storm passes. But the atmospheric conditions that generated that discharge remain. They're building toward the next strike, and the next, and the millions that will come this year alone. Those future strikes will hit a world we're actively transforming. Cities expanding into fire-prone zones, forests drying under changing climate, infrastructure aging beyond design specifications, populations growing in high-risk areas. Each lightning strike will encounter conditions we created. Each fire it ignites will burn through landscapes we altered. The consequences will be ours to face. But consequences aren't predetermined. They branch based on choices. Investing in lightning protection reduces damages. Improving fire management saves forests. Hardening infrastructure prevents cascading failures. Reducing emissions slows atmospheric changes. None of these actions reverse what's already in motion. They just make what's coming more survivable. The Carboniferous world was hostile to modern life. 35% oxygen would poison human lungs. Constant wildfires would prevent agriculture. Lightning frequencies in the billions would make surface activity dangerous. Yet life thrived there. Different life. Adapted life. Life shaped by electrical intensity we can't imagine. That's the ultimate lesson. Earth doesn't need saving. Earth adjusts. Life continues. The question is whether we continue, whether our civilization persists, whether the systems we depend on survive the transformation, or lightning will keep flashing regardless. It flashed before humans existed. It'll flash after we're gone. The bolts don't care about our infrastructure, or our plans, or our hopes. They respond to atmospheric conditions according to physical laws that operate with complete indifference to human concerns. What we do with that knowledge determines outcomes, whether we treat lightning as warning or nuisance, whether we adapt or deny, whether we build resilience or accept vulnerability. The next thunderstorm you experience carries information about temperature, about moisture, about atmospheric stability, about planetary systems responding to changes we set in motion. That information is free, available to anyone willing to observe and understand. The lightning isn't hiding its message. It's broadcasting clearly across every frequency scientists can measure. We just have to decide whether to listen. Because that's what this entire story comes down to. Lightning has always been talking. For billions of years, it's been announcing atmospheric conditions through electrical discharge. Ancient Earth's 5 billion annual strikes proclaimed an oxygen-rich, carbon dioxide-heavy, volcanically active world. Modern Earth's 560 million strikes describe our current atmosphere. Future Earth's lightning will describe whatever atmosphere we create. The frequency will match the conditions will match our choices, and those choices are being made right now.